I think everything's going. I'm going to go ahead and start it here. Um, okay. So let's go ahead and get started. Got people here. I think there's one or two online already as well. So yeah, first of all, kind of sorry for missing some stuff. I had some not feeling too well and family too, so I got a bit behind, but I did get some stuff caught up. So mostly for this class, I think I got most everything back at this point. So if you didn't see, including the test and assignment 4, as well as I went back and looked at some of the assignment 3. So I still have a couple of people on like assignment 3 and 4. So if you're listening to this, do go back and look at the code review, the feedback that I give on the GitHub. A couple of people still haven't responded to fix some issues, but they're not really for most people. It's not really a kind of a major thing. I just have certain kind of requirements about commit messages and things like that I'd like people to at least get a flavor of. So anyway, go back. If you haven't looked at your assignment 3s and 4 in a while, maybe go back and check those out. And also, just in general, as usual, for people, do read the code reviews. If I ask something to be fixed, either now or in future assignments, kind of make certain that you start doing that. So don't keep doing the same kinds of mistakes for assignments and stuff. So yeah, my plan, I was going to, maybe I'll do just a quick one or two things about the midterm test. I don't have a lot to say about the midterm. Almost everybody did fine on it. I didn't have anybody had any real difficulties on it. So that was good. So let me go ahead and bring that up, though, just to mention one or two things. I didn't post an example solution for the test. I could. I was just going to just bring up an example solution and mention a couple of things here. Oh, here. All right. Um, so first of all, let me just mention. I mean, the biggest thing I was doing on the test was there were if you didn't realize that there was actually multiple versions of the questions. I mean, if you were taking the test the way it was intended, you probably didn't know. You should have gotten just one. Should have gotten just 3 questions total. But everybody could have gotten like a different question. There's 3 or 4 versions of each one. So the main thing, a few people did get some points off because I was asking for you to create a notebook and submit that, and everybody did do that. But just in general, make certain whenever you're asked for like a notebook in this class or I mean, in any context, the notebook really should run. I mean, all the cells should run. So a couple of people had notebooks that had some cells that had some syntax errors in them or something like that. So I had to fix something in the work submitted in order to actually either run stuff after it or to infer what it was that they meant. So you probably got 5 or 10 points off for that. So I don't know. I mean, I just usually think of that as kind of a fundamental thing. It's learning to work with Python and Jupyter notebooks like this. really, I guess the main reason on this test is I do kind of wonder exactly how it was that people are developing, answering the questions, developing the code. So, what if the notebook isn't running cleanly, either you're doing it in some other location or you're not really even running the code, you're just typing things in, which would be, in many cases would seem to be a bit risky. But anyway, that was kind of the major thing. So there were like 3 different versions of a question to write a simple function that was supposed to be about doing some NumPy operations, and I don't think anybody that I tested had any problems on that. So, just to let you know. So what I know. And I guess another thing I'll mention is that now that you've seen this, the second test will also be kind of the same format. So so now you'll have kind of an idea of what to expect. Although the second test will be, in theory, will be comprehensive, but it will kind of concentrate on mostly on the stuff that we're going to be doing from support vector machines kind of after the first test here. So most of the questions on the second test will be similar, so you'll get them online, but you'll have to write the stuff in like an IPython notebook and submit the IPython notebook. But it'll probably be stuff over like support vector machines or ensemble learning or using unsupervised learning, which we haven't gotten yet in this class. So that's another thing to keep in mind as you're kind of thinking about or reviewing the test here. So yeah, there's 3 different kinds of. They weren't really meant to be. I would like to have in the future. I'm going to try and improve these questions a bit so that they're at least a little bit more than just sort of toy kind of things. So something that might be actual really useful. But all of them were similar, where you had to make a copy of something and then use. Hopefully, most people. And again, let me know if anybody wants to see an example solution. But I think most people were doing it the way that I was hoping you would. So being familiar with doing things like doing advanced indexing on an array, or just in general using like Boolean indexing or Boolean tests for NumPy arrays in order to extract things and stuff like that. So, and then, for the other 2, and most people finish the test in an hour. Maybe an hour, a little over an hour, which was good. So I didn't really mean for the test questions to be take that long. They're most meant to be kind of a summary. So the other 2 were a linear regression or logistic regression. So the only other thing I'll mention on those, I was mostly just spot checking that you should have gotten exactly and so everybody except for maybe 1 or 2 people didn't have any problems. So for both of these, if you were using a basic either linear regression or logistic regression from scikit-learn, and you just use the default, so even specifying metaparameters, you should have gotten what I was expecting in terms of the fit. For the data that was generated. So, and I guess the other thing I'll just mention that you like for the linear regression, you either were asked to use this function make Friedman, which I have to go and look at the documentation, what that's about, or just the simpler make regression data. So these kinds of functions for generating regression data sets or classification data sets can be useful for testing stuff and things. But yeah, for these 2, I was mostly spot checking that you were doing the right one. If you got the data generated that was asked for, and if you did that, and if you did a model, a default model where you didn't specify any metaparameters, you should have gotten pretty much the exact same fit for the linear logistic regression, and the same regression line for this one, or for logistic regression, you should have gotten the same, basically decision boundary, the same parameters as well. And the same performance on accuracy and stuff like that. Okay, so anyway, in general, good job everybody on that. There weren't any big issues on that, but let me know if anybody had any questions on the test. I can certainly sit down with anybody if they wanted to see something in more detail on this. So I'll leave that leave that there. So I'm not really planning on posting these example solutions, but I'll certainly be happy to go over that if somebody needs to their particular answers for a question or something. Okay. All right. With that, for the rest of the day, then I was going to talk a little bit about support vector machines. So get into our material that we should be working on. So kind of don't forget that we do have our assignment 5 is due already. Yeah. So so I'll also maybe bring that up and see if anybody had any questions in particular on the assignment 5. So I did have that post. I haven't had a chance to check. So I don't know if anybody's experienced any problems or been asking any questions on the assignment 5 yet or not. Actually, I'm going to go ahead and bring that up first. Might spend most of the rest of the time just on that. So. So let me go ahead and just double check all the stuff is working here. So, so yeah, I mean, if you haven't accepted the assignment, started on it, you definitely probably need to do that today here. I haven't checked to see people, how many people, where they're at on this 5th assignment.
Is assignment 5 getting is due on April 3rd?
Well,
That's what
yeah. Did I have the date on that? So, yeah, to tell you the truth, I had meant for the assignment 5 to be over these 2 weeks, the week 8 and 9. So yeah, so I was thinking about that as well. So we really should have another week on this. Let me just check something real quick here. So yeah, my intention was that do that, and we would have. Week on K and then we still have 10, 11. 12, 13. Yeah, I'll have to check the dates again, but let me go ahead and bump that because I know I mean so the usual kind of workflow I meant on these is that that since we started on support vector machines, we should have had till the 10th on that. So we'll go ahead and bump the date on that. So yeah, you still have a little bit of time then if I go ahead and say still next week. Because yeah, we will be talking about, some other materials that we're not going to really have an assignment. So we'll talk a little bit about Bayes, K-nearest neighbors next week, but you can continue working on the assignment 5 next week as well. But bring this up. Yeah. Okay. So if if you haven't started looking at the assignment yet, the format should be relatively familiar for most people. So look, there's like 2 different tasks broken into a couple of subtasks. So kind of like I mentioned before, do go ahead and do each subtask as kind of a separate commit. So there's like 3 subtasks, and then in part 2 we get into using kernels, which I'll try and talk about a little bit today and maybe next week as well. We can continue talking about support vector machines. So if we're doing nonlinear decision boundaries with support vector machines, we can use what are known as kernels. So there are like another, I broke it into 3 main tasks. The second one is relative, just the one subtask, and there's another little 3 subtasks for the task 3. So in general, the first task is doing a basic linear support vector machine on a data set. So load the data and plot it. One thing that I should talk about a little bit today, so if you haven't read through the lecture notebooks, there is a parameter for vector machines, the C parameter, which can be used. It's basically the same thing as doing regularization that we talked about previously in the previous assignment. But it's for historical reasons, they left it in as with this name, the C here. But so you can think of this though as specifying either more or less regularization in order to loosen up or make more strict the decision boundary that the support vector machine is going to do. So for this first data set, when you start on the assignment, if you haven't done it already, you should find, and it's pretty easy, so if you follow, you use a small c initially, and then so both of these for the first 2 tasks will be pretty similar, even though there are 2 separate functions for this. No, there's just one. You just have to specify the parameter into your function. So I guess the only tricky thing on this first one is, you do need to support the third C parameter correctly and be using that when you create your linear support vector machine. So it's what I was going to start. What I was starting to say, this will be. I'll probably repeat some of this here when we talk about support vector machines, but it's a little bit reversed from the alpha parameter. So large values of C are actually giving you less instead of more regularization because of the way that C is defined. So so remember, regularization is kind of like a penalty in order to try and make models, not overfit. So if you have large C, you're actually using less regularization, kind of the opposite of alpha that we looked for. So you'll tend to get things that potentially are overfitting. So yeah, this first data set, when you look at it, there's 1 or 2 values that obviously might be kind of outliers. So it'd be better actually. You might actually get a fit that generalizes better if you use more regularization. So anyway, that's kind of this first task here is just trying to understand this C parameter and how it affects the decision boundary that support vector machines make. So yeah, there's like 2 functions on the first part there. So one just to load the data, and then one to actually create a support vector machine model where you have to pass in the C parameter, and then you use that for both 2 and the part 3 here. So then the other thing on this assignment is we get into this idea of kernel functions. So in most machine learning classes, we introduce kernel functions when we're talking about support vector machines. They are kind of two different things. You can technically use the same idea, a kernel function, in order to use other methods like basic linear regression. You could use a kernel function instead of like the polynomial features that we use in order to get a nonlinear model, right? Nonlinear fit. Right? So for support vectors, for this assignment, we're thinking mostly in terms of classification here. So we're doing a classification problem, but still the same idea. The decision boundary in the first part is just a line, so a linear decision function. So when you add in kernels, it's similar to adding in polynomial features, so that we can actually turn it into we can fit a nonlinear decision boundary. So the reason why these are especially useful for support vector machines, if you read in our textbook, it doesn't go into a lot of detail on this. But the so-called kernel trick for support vector machines makes it mathematically that you can use these kernels without really kind of any overheads. A bit magical. So it's a performance kind of thing. So because of the way support vector machines are defined, you can use them with nonlinear kernels and not have any of the overhead, like creating polynomial features. We were to do it like we did for our previous assignment. I'll try and go into some more details of that in this class or maybe next week as well. But that's really kind of what the second task and then the third task are really about. So there's a particular kernel called a Gaussian kernel, which is related to the Gaussian function. So for normal distributions and statistics, kind of it's related. But the Gaussian kernel is used in order to define a new set of features that we actually fit our support vector machine to. So in short, on the second assignment, we kind of walk you through doing this by hand. So the task 2 is to write a function basically implementing this description here. So you don't necessarily actually have to completely understand everything that's going on. The implementing this by hand is relatively straightforward, although you should be able to do this in a vectorized way. So you shouldn't have to have a loop. I believe that's discussed here as part of the requirement. Is that true? So even though so if you're having some problems figuring out how to vectorize this, how to do this without writing an explicit loop, you could make a first version where you have a loop that sums over the differences between, so this function should be just passing in two essentially vectors of the same size, and you just need to take the difference squared and divide by that, and take the exponent of that, e to the power of that, to get the answer here. So I'm going to show kind of what this is doing here. So if you look through the lecture notebooks, we kind of show what this Gaussian kernel is. But you should also be able to do this by doing a simple vector operation, so like a dot product or something. But anyway, so given that, then the third part is going to sort of walk you through using. So you can use scikit-learn, has built-in ability to use a Gaussian kernel as well as other what are known as these radio basis functions, RBF functions, radio basis function kernels. But one of those, the Gaussian kernel, is one of these different types of RBF kernels. So probably the most common one that's used if you want to make a nonlinear vector machine decision boundary. But anyway, yeah, the third part is kind of using the built-in one and just demonstrating that your implementation should get exactly the same result if you implement this function as described here. So it can be plugged into this here. So I should maybe talk about this in a little bit more detail, but this function here is what is actually needed as a hook into scikit-learn. So it expects to be able to have a function that passes in two matrices. And we didn't vectorize this solution here just to make it easier for hopefully for most people to kind of understand what it's doing. So it's really calculating using your implementation of the Gaussian kernel for vectors and doing that over multiple vectors to get an overall similarity between these two matrices here. Okay. So I think that that's all I can think of for the moment. There's some more details of some things that we can maybe come back to. Maybe once I go into talking about support vector machines and these the Gaussian kernel and stuff. So we can maybe come back to this and see if anybody has any to get a little bit of a better idea of what's happening here, like how this is working, especially on the third task here. So I don't need this anymore, but so. So I do get started on that. So again, for this assignment, I did actually give the meaning to remove that. I did give the Python documentation again. So you don't have to write that, but do reuse these functions. So you do also. So we're kind of back to I guess assignment 4. Also, I've done it the same way like this, even though I switched to slightly different methods. So you shouldn't have to uncomment any imports or anything. So like the top of the notebook is probably already importing all these functions, and stubs have been created for these. So you just simply have to on this assignment fix do the actual implementation. 4 or 5 functions. So let's I'm going to go ahead. Let's jump to new material then. So that's enough for these. We can probably come back to this. So since just to say again, in case anybody came later, I am going to go. I did go ahead and change the date on that, so we still have till next week. We still have till next week to continue working on the assignment 5, and I'll talk next week as well. Maybe some more details. See if anybody had any questions in working out the details of implementing any of those tasks in assignment 5. So sure.
If assignment 5 is directly, what about assignment 6 and 7?
Yeah, so it'll be 2 weeks after that, so I'll give 6 for that, and then we'll end up with the last one So that would end up being over finals week, which was kind of why I was looking at there. But I'll probably go ahead and just leave it like that because I would like to have 2 weeks between. So just plan on 2 weeks for each last two activities. Uh, got I've still got about 20 minutes or so here. So um, yeah, I'm noticing that I had some things misnumbered still, or hadn't gotten them updated with some of the numbering that I had in the course. So yeah, there was just this one notebook on support vector machines. Uh, let me talk a little bit about the C parameters. I only touched on that, but if you haven't looked through the notebook or read the textbook, this is where you kind of get the details of how that regularization works in support vector machines. So just first in general, the difference, support vector machines are a parameterized model. So, they are similar to the linear logistic regression that we spent quite a bit of time with just before we took our test. So, in fact, they have kind of the same set of same idea, the same set of parameters. We just add in some additional concepts. The main one is this idea of the margin for vector machines. In this notebook, if you read through this, we don't go into a lot of details of the actual mathematic kind of background, the differences between the fitness function that's used for support vector machines, how that differs from like the logistic regression. If you're interested in those details, again, I'll remind you, Dr. Ng's class, he goes into a lot more detail about the internal workings of the differences. If I have time, I might go into these, but he actually kind of walks through how you add in to the cost function modifications to support this idea of a margin. They're trying to fit for the support vector machine. So I won't go into those details today, and maybe next week, since next week when we're talking about the K nearest neighbors and the Bayesian, these are kind of really just small, and they're not from our textbook. So next week we've got the two notebooks on K nearest neighbors and naive Bayes, but these are just kind of additional materials. Our textbook doesn't really talk about those, so I might still talk about those one day, and we'll get back and maybe talk a little bit about support vector machines and more details. Anyway, the modifications that are made to the cost function for support vector machines allow you to conceptually think in terms of this kind of classification. So intuitively, the idea is that we start by thinking about a set of data. We're doing a classification task in this example here from our textbook. And here, the classification, the classes are completely separable by a line. So they're linearly separable. Right? So when they're linearly separable, usually there's multiple, there's an infinite number of decision boundaries that would actually give you perfect answers. So just for these two classes, any decision boundary like these two, and any of the infinite ones that kind of goes to that point, or in a lot of other places, would completely separate these two classes. So that just means that at least for the data you train with, it would be able to perfectly classify between the versus color and the Satoshi. So, I mean, not every separator is a valid separator, is a linear separator for these two classes. Right? So of course, there's lots of them that don't, but there are many of them, an infinite number of them, that would actually separate these two classes here. So there's no intermingling of data. So intuitively, if you start with this idea of linearly separable classes, some of these classifiers probably, so some of these decision boundaries probably will give you a better model that would generalize better than others. Right? So intuitively, even though this one separates the two classes, since we're so close here, some data that we haven't seen probably has some petal width a little bit above that, would misclassify. So the intuition behind this idea of a margin is if we select the decision boundary that gives the largest margin, it will be the one probably that will generalize best to unseen data. Because it'll be furthest away, I guess the way I would say it, think of it. It'll be furthest away from the data that we fit it with, so it'll be more likely to, if this data is representative but a bit noisy, other data points will still be kind of around there, still be on the correct side of the decision boundary, if we're maximizing this margin between them. So those changes to the cost function that are done for the support vector machine basically allow it so that when we fit a cost function, it's going to do this. If we have data that's linearly separable like this, the decision boundary that it will end up using will be the one that has the largest margin. So if you pick the points that are closest together and draw a line between them, it'll be the one that's in the midpoint between those lines. It's the furthest away from the two closest points. So again, I'm not going into the details. I'm hand waving a little bit, but for this class, it is that gives you enough of an intuition of what support vector machine is. So if you kind of understand that's really what the cost function for the support vector machine does, you can begin to add in some complexity, right? So for one, for a real data set, it's usually not going to be linearly separable, right? So this is a trivial or easy case. So if I really had data like this, it's pretty easy to fit a model that's going to perform well. It's linearly separable. Be able to make predictions even on unseen data that are perfectly correct or mostly correct. So talking about the parameter here, this idea of hard margin versus soft margin classification. So the first idea when we jump to making the margin more soft is, so for more realistic data, it's not going to be linearly separable. Right? So here we're still using this again comes from the textbook. we're using the iris data set still, but we're using a different breakdown. So Virginica and the not Virginica. So this data here, if you just change it into a binary classification task, is not completely linearly separable. There's no one line you can draw that will separate the circles from the squares. A little bit tough to see here, but there's a bit, some intermixing between the Virginica and the not Virginica iris data set. Just we're only looking at two features, petal length and petal width. So, so the cost function for the support vector machine can still, give you a decision boundary, even if it's not linearly separable, right? So, I guess that's the first thing to understand is that this figure here would kind of imply that we have to find that the class has to be linearly separable, but the cost function still works even if it's not linearly separable. You still get kind of the best margin, the best decision boundary in some sense that maximizes its margin, even if you have some intermixing or overlap, so you can't actually linearly separate the data fitting to. So back to this figure here. So what happens with that C parameter when we add or remove in regularization is kind of the way you can conceptually think of it is it will allow the decision boundary that's selected to either be as strict as possible or to loosen up. And when you loosen it up, so when you add in more regularization, it's as if you're going to allow more points to be in the margin. You kind of ignore that when determining what decision boundary you're going to use, like the cost function. So So yeah, one way of describing that is it's C kind of affects the tolerance or the amount of margin violations that are ignored or allowed by the cost function. So when you have a small value of C, your B-strict, so remember it's kind of backwards from the alpha parameter that we used before. So small values of C mean that you're trying to make it strict. So if the thing is linear separable, you're going to force it to use, there's a particular figure I want to look at here. So yeah, I didn't have these in our lecture notebooks, but here, this is a good one. Is what I'm kind of trying to discuss here. So, especially for outliers, this is kind of probably the best way to kind of understand what the C parameter is doing here, or in general, what regularization does in terms of fitting a classification model like this. So if we have some data that's not linearly separable, like here, but this might be an outlier. So if we try and be strict, so if we end up with a small value C, which will try and give a strict margin, we will end up with some pretty extreme kind of decision boundaries. So we try to take that into account. We might end up with something, you know, that tries and gets like maybe this, right? So we're only getting one thing over the margin. So by regularizing or using that C, you can end up, one effect. This, in general, when we talked about regularization, this is true for the L1 and the L2 regularization. It's also doing kind of the same thing if you think about it for classification tasks. So, if we're doing a linear decision boundary, by adding in more regularization, we're going to make it ignore things that are kind of outliers. So we'll tend to end up with decision boundaries that are more generalizable. Even if we have something that's clearly, or that looks clearly like it's a mistake, some sort of a bad data point, mislabeled or something like that, we would do better on generalizing than we would if we were using more strict margin. Yeah, and the same argument's being made here, although this is a little bit easier to visualize. So here the things are actually linearly separable, but is that the best decision boundary? That's still is potentially maybe mislabeled or some kind of outlier. So decision boundaries probably something like this. Never know, but if that were an outlier, this is going to give you much worse results when you test it than a decision boundary more like this would give you. So yeah, I always mix around which is which. So low values of C are actually being more regularized, so allow kind of more margin violations. And this is exactly the same thing you're doing in the first task for the assignment. The data set we have for the assignment also has a similar idea, like a point or two that's probably an outlier. So use high values of C, we'll try and minimize margin violations, which would have the effect of putting more weight on things that might be outliers. Low value would be more regularized, so tend to be more general of a solution. Okay, so I've got a few more minutes. I'll just mention one or two more things, and then we'll do some more details of this next week as well. Because if you haven't looked through the discussion here, or maybe Dr. Ng's lectures on the kernel trick, this is some good material to make sure that you at least understand from the big level kind of picture. So the only thing I'll say today, kind of to start out with, is that we've already kind of run across this idea. So when we did polynomial regression for the assignment 3, what we were doing is we were adding on new features, remember? So we took the original one feature and we would add on the square or the cubed or the higher level power, right? But those were really just manipulations of the actual single feature that we had, right? So a polynomial kernel, or doing adding on polynomial features is the same thing that we're kind of talking about here when we're building up a support vector machine that can perform nonlinear classification. So like we did for the polynomial regression, you can actually do the same thing. So in the textbook here, they're showing by hand doing what we did for regression, but doing it for classification. So just using a linear support vector classifier, but first creating the 1, 2, and 3 degree polynomial combinations for the data set. So this should be equivalent. This will give you exactly the same thing as using a polynomial kernel. Right? So in support vector classifier, so just a bit about the way scikit-learn uses. So scikit-learn has something called linear SVC, which just does straightforward linear. It doesn't support these ideas of these kernels, RBF kernels, polynomial kernels. So all that's happening for like a polynomial kernel or RBF kernel is similar to like this. So we're taking the same support vector cost function, but we are manipulating the features, so doing something to them so that we can get nonlinear decision boundary. We fit our data. So like we did for regression, when you're using a polynomial kernel for classification, it's the same as putting the polynomial features to some degree, applying a linear support vector machine classifier. So the difference between that and that is that by default, the SVC does nonlinear. So, and if you don't specify a kernel, the default nonlinear kernel used by the SVC classifier is probably the Gaussian radial basis functions. But this should end up getting the same result as the previous one. Just specifying polynomial kernel of degree 3 here using SVC instead of doing it by hand. So the other kinds of kernels that you can use, so we'll talk about the Gaussian radial basis function kernel, or you'll learn about it for your assignment. But the kind of, for a first approximation, you can kind of think of it like this. So, I mean, this is really all the radial basis, what the Gaussian kernel is doing is, if we just have a single feature, we can define different kernels to transform that into a different feature. So here, and so the Gaussian kernel works as a similarity. So if we set a center at -2, this is going to be the similarity. This is going to be the Gaussian similarity between these points and a kernel center at -2. Right? So you'll end up with a maximum similarity exactly at the point when you're applying that, and it will fall off in that bell curve, that Gaussian kind of bell curve shape. The further away you get from whatever kernel you set, or whatever center you set for the kernel, the less similar point is. The original feature is the new transformed feature. So yeah, we'll talk more about this, but all this being done here in this example, if you did the reading, is we're taking a single feature and we're transforming that using a Gaussian function here into two features, x2 and x3. So this data originally wasn't linearly separable, right? So we have two classes again, triangles and squares. We couldn't separate that with a single line. But if we transform that to two features, the same as if we were transforming this into polynomial, the square, or something like that. These values, we could do a similar thing. So we do transformation, so it's no longer, or in this case, even though we're going to use a linear decision boundary, when you transform these like this, it can be the case that they are now things that weren't linearly separable before, when you're using a different set of features, are now linearly separable. This example was made up by hand in order so that they would be linearly separable after we transform them. But in general, if you imply enough of these, you will end up with a representation much more easily separable in a higher dimensional space like this. Okay, yeah, so that's, I'll stop there for today. We'll go into some more details of this next week, plus look at some of those other things as well. Yep, so let me know if people have questions on the assignments. But I will give people till next week to work on that. We'll talk more about it Tuesday. Yes.
Can I ask something?
Yeah.
Yeah. Yesterday I got a grade about assignment 3.
Huh?
After that, I recognized there is something problem mine, so I push it develop commit
Okay.
addressing the issues. So
Okay.
I really apologize about the not for checking earlier. So
Okay. Well, I was put it in the grade book because I was trying to prompt you to go ahead and fix that. So yeah, if you did it, maybe shoot me an email if you haven't. I'm behind on my email, but yeah, I will go back.
Okay, good.
Okay.
Thank you so much.
Sure.
Yeah. Have a good day.